Welcome. So today we are going to start a new chapter. It's called Electromagnetic Induction. Okay. So um, till now we have been studying in electricity. We started actually with understanding static charges, and then we try to understand charges when they move. What is the meaning of electric field? So we also try to understand basically what is electric potential, all that. Then we moved on to try to see what is the relationship between electricity and magnetism. And we also saw that the two scientists, Oersted and Ampere, there are two scientists named Oersted and Ampere. These two scientists actually worked very extensively on trying to establish the relationship between electricity and magnetism. But what they did was trying to see how passing some current through a wire will produce magnetic field. Now we know that if you pass some current through a wire, that produces magnetic field. Like how when you actually take the wire and wind it like a solenoid, you can create an electromagnet also. Okay, so you know that it is possible to do that. So we from electricity producing basically a magnetism is something that uh, these two people worked very extensively on. Okay, uh, Oersted and Ampere. But uh, just soon after that, what happened was there were two more scientists who tried to do the other way around. Is it possible to go from magnetism to electricity? This is the question that basically asked by two more scientists. So one of them was actually a British scientist called as Michael Faraday. You probably know about him quite extensively. Even in your ninth standard, 10th standard, you would have studied that. And the other is an American scientist named as Henry. So these two people worked very heavily on how we can actually convert magnetism into electricity. And while doing so, they actually did no, quite a number of experiments. So we will actually summarize in this three types of experiments done by Henry and Faraday. Okay, and try to understand what do you get out of those experiments? What do you conclude? Okay, so three types of experiment we will see. So we'll say experiments of Faraday and Henry. So experimenter number one. So what is this experiment number one? So they did actually kind of approximately categorized the three experiments. First one, what is this? Let us see. Okay, in the experiment number one, uh, he actually so they one of them both of them have simultaneously did this kind of experiments, slightly differently though. So this actually is a coil. Okay, within this coil is actually connected to a galvanometer. A galvanometer is the device which tells you whether if there is some small current flowing, it will basically do the deflection, and you will come to know that yes, some current is flowing through that. Okay. Now, generally, just if we keep it a coil and just connect it to a galvanometer, there is no battery or nothing is there, so there will be no current, and galvanometer shows perfectly zero deflection. So no deflection. Okay. Now, you take one magnet and bring the magnet from that side to this side. So you quickly bring a magnet into the coil, and suddenly they noticed that there is a deflection. Okay, if you keep the magnet here, there is no deflection. If you start bringing the magnet here, there is deflection. Okay, and if you keep the magnet inside, there is no deflection, zero. Okay. Now you can pull out the magnet. Again, there is a deflection. This time deflection is in the other direction. So while putting it in, the deflection is this way. While taking it out, deflection is this way. But if you keep it inside itself, it is in the middle, the needle. So this kind of a experimentation they did and figured out. And they also found out that while doing so, if they happen to bring this magnet actually very slowly inside, the deflection is not very high, small deflection. It's just deflect a little bit. Okay, the needle. Okay, and Suppose if you bring it very fast, then deflection actually is more. Okay, the more current. So these are the kind of experiments they did, and from that they realized a lot of things and they summarized it in the form of laws. Okay, so this is one experiment. Let's look at what is the second experiment. So second experiment is that they replaced this magnet with actually a coil connected to a battery. Okay, there is a battery and there is a coil here. Now we already know that if you actually connect a battery to the coil and pass some current through this coil, it produces magnetic field around. So there is magnetic field here. Like how there was magnetic field around the magnet, same way there is magnetic field around a coil conducting current also. Okay. Now you bring this whole system towards this, the coil, towards the other coil, very fast. Okay. Suddenly you can see the deflection in this. And when you take it out, you see the deflection. But if there is no relative movement, if you are just keeping it either here or very near or very far, wherever, there is no deflection. So deflection happens only if there is actually a movement. Okay, that is what is observed. Now that is experiment number 2. In the experiment number 1, you saw that it is only the magnet is moving. In experiment number 2, you are seeing that it is an electromagnet that is moving. I mean basically there is absolutely no physical magnet here. You're just passing electricity and magnetic field is produced here. So it's not about physical magnet, it is about the magnetic field. That kind of conclusion you can come here. Okay, and then third experiment is even more interesting. In the third experiment, what happens is there is a coil that is kept, okay, which has a galvanometer connected here, and there is no deflection. Now there is one more coil that is kept by the side of it. Okay, and this coil now has a battery connected and a switch here. We are not going to move the coil at all. None of the coils will be moved. Instead, they observed that if you switch on the switch, at that instant you can see there is a deflection in this. Okay, after switching it on, it will be in the on position for some time. Okay, when it is in the on position, current is flowing through this, and this has given rise to magnetic field. But that is not causing the deflection, because deflection has returned back to zero. Deflection came only when there was a switching on. While switching on, we saw the deflection. After switching on, there was no deflection. Okay, now surprisingly, when you switch it off, while switching off, you saw the deflection again. This time the deflection is on the other direction. So if the switching on deflection this way, switching off deflection is the other way. Okay, but there was deflection. But after switching off, there is no deflection. So what does it tell us? If there is a deflection, it simply means that current is getting basically produced in this coil. So that means that if there is actually, while switching on, current is getting produced in this coil, okay, where is no connection between this coil and this coil. Okay, they are separately kept far from each other. And while switching off, current is produced, though in the opposite direction. So these are some very nice things that they have uh, found out. Okay, they have experimented and found out. From that, they could conclude a lot of things. So, for example, they concluded that it is not about physical movement of the magnet, because here there is no physical movement. So, in the first one, there is a physical movement. Here, there is no physical movement. So, which means that even without a physical movement, electricity is getting induced into this. There's some current is coming into this. What does it mean? But if there is if you switch it on, if the current is continuously flowing and it has become a strong magnet, even then there is no current here. That means if in the process of basically switching on, the current now actually starts flowing and magnetic field around it starts building up. So while the magnetic field is building up, okay, then there is deflection. And while the magnetic field is tearing down, from going away, going off, then there is deflection. That means that the magnetic field in this area, when it changes around this coil, if the magnetic field changes, that gives rise to the induced current. Current gets induced into the coil. So the magnetic field can change for two reasons. One is there may be a relative motion. Even when there is a motion, there is a magnetic field around which is changing. Or magnetic field may be changing because the current inside this is changing. If the current inside this is changing, naturally magnetic field around this also is changing, because we have studied that magnetic field can be calculated using the current flowing through that. Okay, so these are the three important experiments they did, and they came to conclusions. And Faraday came with certain laws. Okay, before getting into Faraday's law, because he uses a word magnetic flux in his law, so we are going to understand what is this magnetic flux. Okay, magnetic flux is like electric flux or any other flux. Basically, is if you take magnetic field as B, okay, if there is a magnetic field like this B, continuously it is all there everywhere. Okay. Now, if the magnetic field is going through a certain area, okay, some area, let us say some area through which magnetic field is going through, you can ask a question that how much is the flux passing through this area? How much is the flux passing through this area? You can ask that question. So flux is about that. Okay. So what we do is we calculate the flux through this area as product of B, that is whatever is the magnetic field, into the area. So we always say flux is equal to magnetic field B, okay, and into area. So I'm just using the word into here. This is not a I'm going to write here in the place of this a small dot. Okay, I'll tell you why I am writing the dot. So B into area. So if you just find out how much of flux is passing through this, it's like water going in a pipe. If you know how much of water is flowing per minute or something, you can find out for the whole area how much is going. Just multiply with the area. So like that. So this is also multiplying with the area. The flux can be calculated. But however, you have to understand one important thing. Okay, let's say if you are going, if there is a pipe, okay, and if you know that the water that is coming out of that, okay, you can say that water is flowing what in this whole area as, let us say, per unit area, it is 8 liters, or rather 2 liters of water per unit area. I will call it as water flow. Okay, water flow density. Okay, I'm just basically using one new word. I don't even know whether this is the correct word. Water flow density we can use. Okay, so is equal to 2 liters per unit area. Okay, 2 liters per unit area per, let us say, second. What does it mean? If I take a unit area here, means 1 centimeter cube or whatever unit area. Okay, in that, if you calculate how much water is coming out through passing through that area in 1 second, okay, take that much of water, it will be measuring 2 liters. Now when this is given to you, if you want to calculate total water flux through this, okay, what would you do? Total water flux is equal to, if you see, this is 2 liter per second, okay, uh, per unit area. So total area is, let us say, A. Then I will say 2 into A. Correct? So per unit area it is 2 liters, means total area it will be much more. It is like saying that the same kind of a small volume, you can say, so many, how many of them are there, that we are finding out. Now with that being there, okay, what if I take the area? Okay, see, in this case we are very clear that the flow is in this direction, okay, and the area is perpendicular to that. Okay, instead of that, if I take a area like this, I will cut the pipe slightly differently. Yeah, I will do one thing. I'll take this pipe here and I will cut it like this area, and I will say the water is coming out of this is water flux. If I want to calculate this, how will you calculate? Remember, whether you cut it like this or whether you cut it like this, the amount of water that comes out per second will be same only. Just because you have cut it like this, more water will not come per second. Okay, because that's all is coming from this side. Now that means what you have to calculate is, now this area you cannot just multiply. This area is a bigger area. If you multiply this area, then you get it wrongly. So what will you do? You still have to multiply this area only. Okay. So now what we do is actually to find out this area, it is like a triangle. Okay. And we take the angle. So let us take this angle. Okay. This angle. And if you take that angle, okay, then this area into cos theta is this area. Adjacent, this is theta. Okay. Adjacent by hypotenuse. Let's say A, B. I am taking the diameter of the area. Okay. Diameter, if you multiply later, like pi r square, pi d square by 4, that will be the area. So we will take the diameter of the area. So A, this is AB, this is, let us say, AC. You can clearly say that AB by AC is equal to cos theta. So if you want to calculate AB and if you are given AC, you can say AC cos theta. So instead of that, we can actually say perpendicular area is equal to given area A into cos theta. So then we will get the perpendicular area. Okay, in our case, we have also seen that in earlier scenarios, the area has been basically presented as a vector. Okay, remember, area has been presented as a vector. So we always, whenever we see an area, okay, some area, so the area, let us say, is whatever, some 0.5 meter square. Okay, then we will actually write a line perpendicular to this area. Okay, with a length equal to 0.5 and call this as a area vector. We always represent area as a vector which is perpendicular to the area. Okay, so this area is now represented by a vector which is perpendicular to the area. We will call that as, let us say, vector A. I will call this as vector A. This is vector B already there, and this need not, this vector a vector may not be always perpendicular. In this case, the area whatever you have is, area vector is this and B vector is this. So there is an angle between them. So we have to use, as we did here, is equal to cos theta. Like how we had to calculate the perpendicular area. To get the area which is perpendicular to the B, we need to do a cos theta on it. Okay. So what we are saying is that if we want to calculate the flux, okay, so we have to have B into A into cos theta, that is the angle between B and A. Okay, so which is actually written as, this is as a dot product B dot A. So flux is nothing but B dot. If you remember, in the vector algebra, you would have figured out that dot product is mentioned as B dot A is called as BA into cos theta, like that. Okay, so flux is defined by the total amount of total B that is passing through this. However, we will consider the angle and say it is B dot A. Okay, we just don't say B into A. That is the definition of a flux. Now, why do we need this? Why do we need this flux? Now, if you look at a plain area, it is somewhat easier. Okay, this area is like a simple plain area, and B inside that, all of them basically have the same angle with the area. Instead of that, if you had an area which is very different kind of a shape, so here you can see the area is like a some shape. This is the shape of the area. Okay, this shape of the area. So this side you can see everywhere there is the inside, there is a curve and all that. So this shape of the area means that if you take any small, see if the B is coming like this. Okay, this is our magnetic field lines coming. So then any small area you take, okay, it will have a different angle to B. So you will have to actually split that into multiple areas. Okay, so we will generally mention flux, that is why, as the addition of all that. Okay, every small piece you take, multiply it by the A there, and take the next piece and multiply it by the A there, and like that you add all of them. So we will use the word summation for that. This is nothing but addition. So do not get always worried about this symbol. This simply means addition. Okay, I'm going to add all the small pieces. Okay, for all small pieces, for all n, I'm going to say bn dot an, like this. Okay, sometimes we also use the word not a but also dA. Okay, the reason we say dA is because it's a small area like that. Okay, d means we generally use for small, dan. So this is our flux. For all small pieces we add it and we'll get a flux like this. Now what is the use of this flux? So next step is to understand why do we needed this flux and how Faraday used this term. Okay, so we'll talk about that. Now let's go to the next step. So what is Faraday's law of induction? So after doing all these experiments, Faraday concluded that he can now make a law, because his law is stated like this. So let's state the law. The magnitude of induced EMF, the magnitude of induced EMF, okay, in a circuit is equal to the time rate of change of the magnetic flux through the circuit. Any circuit you have, let's say you have a wire, you take a wire and make a circuit like this. Okay, now if there is a magnetic flux that is there here, okay, if there is a B that is going through this B, okay, he says that how much that B is varying. See, the time rate of change of magnetic flux through the circuit. So you can calculate the flux through that circuit. In a sense, in this area, how much flux is going. So if that much flux is basically changing with respect to time, if it is not stationary but it is changing with respect to time, then that will be the exact amount of EMF that gets induced. Exact amount of EMF that gets induced. So he made this mathematical statement: EMF induced is equal to minus d phi by dt. Okay, look at this, the meaning of this. The phi is flux. Okay, flux is written as phi. Okay, d phi by dt means, as we studied earlier also, this is the differentiation of phi with respect to time t, which tells us what is the rate of change of phi. Like when we talk about rate of change of displacement, rate of change of position is velocity. Rate of change of velocity is acceleration. So whenever we use rate of change of something, we use differentiation. So here also d phi by dt means rate of change of flux. So we are using d phi by dt is equal to E. That is the induced EMF. That means if you actually do lot of changes in the flux, very fast changes in the flux, then you are going to get a induced EMF E. Okay, which is more. If you slowly change it, induced EMF will be there but less. So it will be equal to how fast it is changing, not how much is there. Remember this. It's not about how much is there. It's about how fast it is changing. Okay. And then the negative sign here basically indicates that it is induced in the it tells you the direction. The EMF is induced in the direction that is actually opposing the direction of change in the magnetic field. So what does it mean? So this law actually comes out as Lenz's law. Okay, we will talk about that a little later. So how to calculate the EMF, I will explain to you. Okay. So however, this is consider that this is actually this minus is because of the Lenz's law. Okay, but Faraday generally stated this. Okay, and suppose if we had a wire, okay, which instead of single wire you had, let us say, multiple turns, multiple round of this wire coil and then taken out. Okay, let's say n rounds of the coil. Then each round will generate this much, minus d5 by dt. If you had n round, it will generate n into minus d5 by dt. So total generated. So this is how magnetic field can generate electricity or electric current or electric field. Okay, so we basically talked about how Lenz's law will happen. We'll come to that. Now, most very important thing is now how much EMF gets generated. How much EMF gets generated depends on what all factors. Okay, so how to obtain a large EMF? If I want to get large EMF, how to do that? Very simple thing. Okay, what are the things you can do? You can increase n. That means more windings if you put, you will get more EMF. Okay, if you actually, on the other hand, also can increase d5 by dt. How do you increase d5 by dt? So d5 by dt means change in flux with respect to time. So let us say flux, you can go. A flux actually is also given in what we call. So it's Tesla, and it is meter square. We can say Tesla meter square. Or there is one more word called Weber's unit. Okay, so let us say you are having flux of going from 5 Webers to 10 Webers. So flux is varying from 5 Webers to 10 Webers. Correct? In let us say 2 seconds. In 2 seconds. In this case, what is d5 by dt? d5 by dt is final minus initial. Okay, that is phi1 minus phi2. That phi2 minus phi1. Okay, so let me write it as delta phi as, so we can write it as delta phi by delta t also. Okay, delta phi by delta t is the more approximate form, and d phi by dt is the derivative form, which is more exact form. Okay, delta phi is equal to phi final minus phi initial divided by, so that is delta phi. Okay, delta t is basically time taken here. Okay, so you say, I will say delta phi by delta t is equal to 10 minus 5 divided by 2, which is nothing but 5 by 2 is equal to 2.5. Correct? So the answer is E is equal to minus 2.5 volts EMF generated. So if you forget minus, basically magnitude of the E is simply equal to 2 volt, 2.5 volts. If I want to actually, let us say, increase that, what would I do? I would do it as one, I said n I can increase. The other one is basically I can increase delta phi. I can go from 5 to 15. Okay, then this will become basically 10 by 2 and it will become 5. Or I can decrease the time. That means I can go very fast. I can say same as 1 second. If I use 10 minus 5 by 1 second will become 5. So either I can decrease time or increase phi. Okay, remember that. So if you go, for example, if you have a very powerful, extremely powerful magnetic field, okay, and if you are, let us say, going from 100 Webers to 105 Webers in 1 second, okay, or if you are going from 10 to 15, in both cases the EMF induced will be same, because the difference is same. Just because you have a very high magnetic field does not mean you can generate a very high voltage, okay, or very high EMF. So it is dependent on the difference only, difference and time. Okay, remember that. That is how you can actually calculate. So now let us try to calculate some. Okay, then we get a better picture. Okay, a square loop of side 10 centimeter and resistance 0.5 ohm is placed actually vertically in a east-west plane. Okay, a uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. So the magnetic field is decreased to zero in 0.7 seconds at a steady rate. Determine the magnitude of induced DMF and the current flowing through this. So what I am going to do is I'll try to picturize this. Okay. So please understand that we are trying to write a 3D pictures and have to be a little more careful while writing. Okay. So I am going to write here. Let's say a top view of what experiment we are doing. So I am going to do the experiment on the floor, okay, and I look at that on from the top like this. Okay, so when I look at that from the top, I am seeing that this is east and this is west and this is east and this is north and this is south. Okay, and the coil is kept. How it is kept? It is kept in the east-west plane, in this plane. Okay, so so let's say the coil is a square coil like this, square coil. Okay, so this is 10 centimeters. Each side is 10 centimeters. But when you keep it here, okay, when you talk, if you keep it like this in the east-west plane, okay, and I am seeing it from the top, I will only see the line, one line. So I'm going to write that line. This is the thickness, let us say. That's all. This whole thing is 10 centimeters from here to here. So this coil is like this actually. I'm seeing it from the top. Okay. In between there is space. Okay, you can see. Like this is how the coil actually is. Okay. Now, what they are saying is that a uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. Okay, across the plane. So everywhere in the northeast. Northeast is actually exactly between these two, 45 degrees. This is northeast, correct? So in the northeast direction, we have put in, set up actually a magnetic field like this. It's passing through, the whole magnetic field is passing through this. Uh, so all over the place, it is vertically, it is there, and everywhere magnetic field is going through that square like this. Magnetic field is going like this. Okay, only thing is it is not going perpendicular to this, it is going at an angle, and the angle we are sure is actually 45 degrees, because northeast is middle of north and east. Okay, with that now you can see that we know the B angle of the B with respect to this. Okay, the question is that if you just keep it like this, inside the coil there will be no magnetic field that gets induced. Okay, because there is magnetic flux and coil is simply sitting. If the magnetic flux is not changing, delta phi by delta t is required for us to get the EMF. So EMF actually equal to minus of delta phi by delta t. If we know delta phi, if we know delta t, we can calculate. So what is phi? So delta phi by delta t actually nothing but phi final minus phi initial divided by delta t, time taken. So we know that what is the final, what is the initial phi. So they have said what is they have set up here. Okay, so that is B. They have given B. Magnetic field B is equal to, they have given it as 0.1 Tesla. Okay, and we know the area of this actually is equal to 10 centimeter means 0.1 meter into 0.1 meter square. That is the area. Okay, and what is the theta angle between the B and A is 45 degrees. Therefore, phi is equal to, phi initial it will say, is equal to B into A into cos theta, which is nothing but, okay, 0.1 into A is 0.01 into cos theta is cos 45, which is nothing but, this is, I will write it as 10 power minus 3. This I will write it as 1 by root 2. This is phi initial. What is phi final? Phi final is 0 because they are saying that from that place, from that it is decreased to 0. So we will substitute that, minus of phi final is 0 minus phi initial is 10 power minus 3 divided by root 2 whole thing divided by delta t. They have given it as 0.7 seconds, 0.7 seconds, correct? So you can calculate this. This would be equal to, okay, minus into minus plus 10 power minus 3 by root 2 into root 2 into 0.7. Okay, root 2 into 0.7 is approximately 1 because 1 by 0.7 is actually not root 2, but if you put root 2 down here, okay, so root 2 is 1.414. 1.414 into 0.7 is approximately 1. Okay, so I will write this as 10 power minus 3. This is what? This is EMF induced. We will call this as volts. EMF is volts. So 10 to the power of minus 3 volts is induced. So what is the current? Current, for that we have Ohm's law. Okay, current is equal to EMF induced divided by resistance, which is 10 power minus 3 divided by, what is the resistance given? Resistance is given as 0.5 ohms, 0.5, which is equal to 2 milliamps. 2 into 10 power minus 3 amps or 2 milliamps. So that is why you can, that is how you can solve the question with respect to a problem given in terms of B and A and the angle between them, and you can calculate phi. We know phi initial and phi final, and you can calculate delta phi. If they are given delta t, so you can delta phi by delta t can be calculated. That is nothing but the induced EMF. This is how you can calculate induced EMF. Okay, so let's do one more question. So take down the next question. A circular coil of radius 10 centimeters and 500 turns of resistance 2 ohm is placed, okay, with its plane perpendicular to the horizontal component of the Earth's magnetic field. So Earth's magnetic field is there, okay, so it is not even put in any magnet, it is just rotated here in the room without a magnet. Just take a 500 turns coil, okay, with 2 ohm resistance and rotate it. So when you rotate it, because there is a Earth's magnetic field, it produces a little bit of small EMF. Okay, and how much is that? That is what we are asked to find out. And it is basically you are asked to estimate this rather than accurately calculate this. Okay, so how do I write like that? So there is a you have to have plane perpendicular to the horizontal component of the earth. So let's some horizontal component of the earth's magnetic field. Let us say I will write it BH, earth's magnetic field. Okay, now what we have, a circular coil of 10 centimeter 500 10 centimeters radius. Some circular coil is there like this. Okay, and this 10 centimeter radius circular coil actually uh, is rotated. Okay, there you see this is actually rotated uh, in the vertical diameter. That means I have my vertical diameter. This is my vertical diameter. Okay, along this diameter it is actually rotated like this, like this. So if you have a coil like this, let's say this is my coil. Okay, let's use a coil here. This is my coil. Okay, now Earth's magnetic field is like this, and I'm going to keep it here, and I'm going to rotate it like this. Can you see this coil? I'm going to rotate it like this. I'm putting it in front of this. If you have a background issue, you can see like this. Okay, now when a coil is rotated like that, question is that we are not continuously rotating. We are only rotating it by 180 degrees. That means if the first coil is like this, I'm going to rotate it one round. That's all. Just from 0 to 180. Now 2 rounds means if it is coming back to the same position means it is 360. So I'm not doing that. I'm just doing half round. Okay, 180 degrees. So 180 degrees when you rotate it, how much is the EMF that is produced? So they have given us actually the B of Earth's magnetic field, which is nothing but 3 into 10 power minus 5 Tesla. A very small magnetic field. Okay, and the turning time taken is basically delta T is 0.25 seconds. Okay, now let's calculate phi. Phi initial. Initially, how much is the phi? B into A into cos theta. B into A into cos theta. So cos theta means in this case, this is perpendicular to this line. So your area vector also in this direction. B vector also is in this direction. So angle between them is actually 0. Okay. So we will say BA cos 0. I'll write it as cos 0 as 1. So nothing to worry. BA. And what is A? B is given as 3 into 10 power minus 5. A is given as they have given a 10 centimeter radius circular coil. 10 centimeter radius circular coil. So that means that pi into 10 square. Okay, pi into 10 square. 10 is centimeters, so I will write it as in meters. Pi into 0.1 square. That is the radius. Okay, cos theta is not there. The 1. So this is BA initial. Okay. So what is BA final? So I'm just going to basically write this as a 3 pi into 10 power. 0.1 square is 0.01. So 2 more. That means 10 power minus 7. This is BA is. Okay. So I'm going to write phi final is equal to, now BA cos theta means BA into cos 180 now. Cos 180 is minus 1. So this whole thing will become just minus 3 pi into 10 power minus 7. Now EMF induced actually equal to minus of n into d phi by delta t. So n is how much? N is 500 turns. So minus of 500 into, okay, delta phi is how much? Phi final minus phi initial. So which is minus 3 pi into 10 power minus 7 minus 3 pi into 10 power minus 7 whole divided by delta t is given as 0.25 seconds. Okay, so this one, if you see, calculate. So this will become twice of this. Okay, so twice of that actually means uh, 6 pi. Okay, 6 pi. So minus, you can take it out and cancel it, minus into minus plus. So 500 into 6 pi into 10 power minus 7 by basically 0.25. So that will be same as saying that if you take it up here, it will be 4. Okay. So 4 into 500 is 2000. Okay, I will write it as, here I am going to continue, is equal to 2000 into 6 pi into 10 power minus 7, which is also equal to, okay, which is equal to so we'll come to basically 10 power minus 7 into 2000. 3 zeros I will take it here and make it 4. So 2 into 6 is 12. 12 pi into 10 power minus 4 volts. Or we could say basically as, we can also say it as 120 pi, sorry, not 120 pi. So 1.2 pi into 10 power minus 3 volts, which is pi is 3.14. 3.14 into 1.2. You can calculate and say, I will write it simply as 1.2 pi millivolts. You can calculate that. Okay. So this is basically the voltage that basically the EMF that gets generated. Now, if you want to calculate the current, you have to divide it by the resistor. Okay, so I'm going to say that this will turn out to be about 3.8 millivolts. This is 3.8 millivolts. If I want to calculate current, that will be equal to EMF divided by resistance. Okay, so resistance is given as 2 ohms. So 3.8 by 2 ohms, which is equal to 1.6 milliamps, is the current. So just a quick repetition, what we did was we actually calculated initial and final flux. So that is my 0 degrees to 180 degrees, and whatever is the change in flux divided by time we calculated. We got the rate of change of flux multiplied with by n, so that the n terms are there. So you will get the EMF negative of that, and that divided by resistance will give the current. So what is important here is that this is an estimation. This is not very accurate. The reason it is not very accurate is because you can see here when it is turning, okay, it is not always actually changing equally. Okay, it is not a linear change. When it is moving from let us say if it is turning around like this, when it is actually going from this kind of a um, path to like this, okay, so in between when you come here, it is not even actually change flux, cutting the flux at all. Okay, here it is doing maximum. So the way it is doing here is not a very uniform thing. Okay, so whenever when it is in an angle, the B dot A is not exactly same. Okay, B dot A is keep varying with respect to the time depending on the angle. So because of all that, we only took final and initial. So if you take at every point, then the values will become slightly different. Okay, so this is an estimate of how much it could be approximately. Okay, so this is sufficient. You see here, it is going to give you almost 1.6 milliamps of current. A small LED may even light up, very small LED. Okay, if you can put, provided you have that many number of turns, just by the Earth's magnetic field rotating it. Okay, so that is basically how you can calculate. Now, so Lenz's law and what we call conservation of energy. Okay, Lenz's law and conservation of energy is a very interesting topic. So we will say that energy actually gets conserved always. This is a conservation of energy is a more universal law. Okay. Here we are talking about Lenz's law, which simply says that uh, when you have a magnetic field that is changing around the coil, it generates certain EMF or current. Okay, and the direction of the current will be such that it is opposing it is opposing the change in flux. That is Lenz's law. Lenz's law says that change the EMF direction of the EMF is such that, okay, it is opposing the change in the EMF, whatever it caused it. It opposes the change. It opposes the thing that caused this. Okay, that is called Lenz's law. Why is it a conservation of energy? How can we say that this is actually conservation of energy? So we'll discuss this in the next session, and we'll also do some questions to basically able to guess in which direction the magnetic field gets no, the in the electric field gets produced. Current flows in which direction. So these some of the questions are very stock questions in competitive examinations. Next session we are going to work on that. Thank you.